Hi, today we're talking about section 8.5, independent events. The book immediately starts talking about Amanda and Brian. They both have a coin and they are going to be flipping that coin, each of their coins, and they want to find out what's the probability they will both get heads. So you have two events going on. Amanda's flipping her coin and Brian is flipping his coin. And those two events do not depend on each other. So they are independent events. Amanda's got her coin up here and her probability of getting heads is 1/2. 1 out of 2 chances. Brian's probability of getting heads is also 1/2. Now before, we would just add up those partial probabilities and call it good. But that was when one of the events was dependent on the other. Here, these events are not reliant on each other. So this tree diagram right here shows what I'm talking about. Amanda is independently flipping her coin, and if she gets heads at the very same time, Brian could be over there flipping his coin and he gets heads or tails. So here our outcome is heads, heads. Here our outcome is heads, tails. Now if Amanda gets tails, Brian could get heads. And so our outcome becomes tails, heads, or tails, tails. So we really, out of the 4 possible outcomes that could happen, only one ends up being both heads. So how do we get to that mathematically? Like, what operation do we need? How can we get 1/2 and 1/2 and get 1/4? What needs to happen right here? Well, hopefully you can see that that needs to be multiplication. If you are looking at the probability of independent events, you take the probability of event A and you multiply it times the probability of event B. So the probability that Amanda would get heads is 1/2 times the probability that Brian will get heads, 1/2, and that will get you a 1/4 or 0.25 or 25% chance that they will both land on heads. So how do I know when I need to add or multiply my probabilities? Looking at this right here. How do I know? I can simply ask, does one event influence the other event? Does one event influence the other event? Hopefully you can see that Amanda's coin flipping isn't affecting Brian's unless she's throwing it at him or something. But there's nothing in the problem to indicate that she's doing that, so they're independent of each other. If we can say yes to that, they do not influence one another, or I'm sorry, if we can say no to that, does one event influence the other? Ooh. Does one event influence the other? No. If we can say no to that, then we multiply. All right, so in this example, Amanda was given a jar of marbles containing 5 red, 2 blue, and 3 yellow. Amanda is going to draw 2 marbles from the jar, but she's going to replace the first marble before she draws the second one. Amanda wants to know the probability of drawing a blue marble both times. So she's going to draw it once. So the first draw, there are 2 blue and 10 total marbles. So that's going to equal 1/5. That's our probability of getting blue on the first draw. Now in past examples, we would have said, now we only have 9 marbles in the jar. But now we're being told she's going to put that blue marble back in if she gets it. So on the second draw, we still have 10 marbles. Nothing has changed. And there would still be 2 possible blues. So the second event is not dependent on the outcome of the first event. They are independent of one another. So we have independent events, so we need to multiply. 1/5 times 1/5, and the probability of getting 2 blues would then be 1/25. Okay, so moving on to example 8.5, this is from page 390. Coupons for a free food item and ride were randomly distributed to each of the first 60 people at a county fair. Each person had an equal chance of receiving a coupon for one of the following food items: hot dog, turkey leg, cotton candy, or ice cream. And I'm going to underline that. We have hot dog, turkey leg, cotton candy, and ice cream. So there are 4 foods. Each person also have an equal chance of receiving a coupon for one of the following rides: Ferris wheel, teacup, and carousel. Now there are 3 rides. What is the probability that the first person received a coupon for a turkey leg and the carousel? So each person, the first 60 people, are going to be getting 2 coupons when they get in. One is going to be for a food item, the other is for a ride. Remember, sometimes you'll have to read a word problem multiple times for understanding, so make sure you understand what it is that's being asked. We want to know the probability of getting the turkey leg and the probability of getting the carousel ride. Now, the one ticket, if they get a turkey leg, that's not going to affect the ride ticket that they get in any way. These are independent events, so we need to multiply these. The probability of getting the turkey leg is going to be 1 out of 4. And the probability of the ride is going to be 1 out of 3. So the probability of getting both the turkey leg and the carousel is going to be 1/12. All right, moving on. What is the probability that the first three people all received a coupon for the Ferris wheel? I guess I struggle with it because it seems like our number of tickets for the Ferris wheel is going to be decreasing, changing the probability with each new customer. But that's not how the book wants us to think about it. So we'll press on. All right, so apparently we have the first three people, and they are going to get the Ferris wheel each time. So the probability of the Ferris wheel for the first person, probability of the uh, Ferris wheel for the second person, and the probability of the Ferris wheel for the third person. They are mutually exclusive. According to the book, they're not going to affect one another. So we have a 1 in 3 chance. Maybe it's a spinning. That's how I'm going to do it. I'm going to modify the story. Instead of it being coupons, it's going to be a spinner. Now it truly is going to be, they get to spin for a free food item, and now they also get to spin for a free ride. So we get 1/3 times 1/3 times 1/3, because spinning it isn't going to affect anything. I hope I haven't confused you, but that really was baffling me. If I have, just to make sure you understand, if I have 2 coupons and one's for the Ferris wheel and one's for the carousel, and I give the Ferris wheel ticket or coupon to the first person, well, now suddenly the probability of the second person getting the Ferris wheel is not going to be independent. It's completely dependent. And it's for the second person to get the carousel, it's going to be 100% for that second person, because that's what's left. So I like spinner. So we're going to go to spinner. We're going to change it to spinner. So the probability of the first person, second person, and third person all spinning the wheel and getting the Ferris wheel is going to be 1/3 times 1/3 times 1/3, which equals 1/27. All right. Finally, what is the probability that the first person did not receive a coupon? So we're going to change that to spin. Did not spin and get the ice cream or the teacup ride. So now we're talking about the probability of not getting something. So hopefully you see that they're really asking the probability that they got either the carousel or the Ferris wheel, or the probability that they got all the other foods except for ice cream. That's the complement. Hopefully you remember that. That's a couple lessons back. But the probability of the complement for ice cream and the complement for the teacup ride equals the probability for the complement of the ice cream times the probability of the complement for the teacup. Now, to get a complement, you subtract the probability of that event from 1. Remember the probability, if you add up all the partial probabilities, you're going to get 1. So we go 1 minus the probability of getting ice cream is 1 out of 4 times 1 minus the probability of getting the teacup ride, which is 1 out of 3. This will leave us with 3/4 times 2/3, which equals 6/12, or 1/2, or 0.5, or 50%. All right. Hopefully that makes sense for you. Good luck with your homework, and I'll see you next time.